Our project is Automated Robust Stacking of Prisms, also known as Prism Bot. I'm Ethan.
I'm Kenneth.
I'm Annie.
We care about stacking because stacking is a cognitively challenging task. There's applications of stacking in construction and fabrication. We focused our problem on stacking prisms. Prisms are easier to grasp and stack compared to arbitrary objects due to their simple geometry and flat surfaces.
All right, so our initial method was mostly adapted from the bin picking notebook, but as you can see, it was not very robust. It could not robustly grasp objects or even place them down precisely enough to build a tall stack. So in order to mitigate this, we use a state machine. The state machine robustly clears the space where the stack is going to be built by detecting when the stack falls over so that we don't end up stacking over fallen debris, which would render an unstable stack. We also use self-correction when motion tracking error is detected so that the trajectories that we execute are the trajectories that we expect. We also do center of mass calculation so that we can precisely place the blocks such that their center of masses line up vertically. Recall from class that we can estimate center of mass by lump parameter estimation. If the object is held still, in fact, it's possible to calculate the terms separately and separately calculate the mass and the center of mass of a held object just by looking at the external torques of the EWA. The only problem is that only the x and y coordinates of the center of mass of the object are identifiable in the world frame, since the z coordinate is in the direction of gravity. The solution is to just measure from two poses and use a mathematical program to find the optimal center of mass that matches up with the measured external torques.
So another problem we ran into in our initial methods was problems related to grasping. Our main problem was that we would often try to grasp points that were near edges. So our grasps would either fail, or if they succeeded, they would often be wobbly and would result in poor placing. So the way we fix this is to develop an edge heuristic so we can avoid grasping near edges. So the way it worked is that after we picked a target grasp point, we would sample the 25 closest points spatially from our point cloud and collect their normals. And then across these 25 normals, we would find the minimum dot product between any pair, and we would have a cutoff because for a face, this heuristic would give us a large value since all the normals would point in the same direction, and we would get a lower value near edges because we'd have normals from two different faces, which would result in a lower dot product. We also improved our perception by adding segmentation. We used the DB scan algorithm to segment objects spatially, and we also segmented them via hue to account for the case where two objects were touching each other. And this let us detect which objects were in the stacking zone and move them away. And it also helped us pick the order of blocks to stack.
For our final results, we evaluated our system by testing it on 10 trials with varying number of objects and object type. So you can see here that we tested 2, 3, 4, and 5 rectangular prisms, and the same for pentagonal prisms. We have a high success rate for less than or equal to 3 objects, which is a greater than 90% success rate. However, as we increase the number of objects, we can see that the success rate drops. And for pentagonal prisms, the success rate also drops. One common error that we saw, especially for a large number of objects, was a simulator crashing due to the high number of collisions that are involved when the stack gets taller. Here you can see our system working in full. First, our robot clears the object from the stacking cylinder so that it could replace it with more precision. Now you can see for each object, our robot rotates the object a bit in order to do the center of mass calculation to again place it precisely on top of the preceding one. In this simulation, our robot is able to successfully stack 7 objects on top of each other. And we think that this is actually the maximum that is possible for our current simulation. As for the 6th block, it is currently not visible to the top. The top of the block is not visible to the cameras. Thanks for listening. Our code is publicly available on GitHub for others to build on top of.